So, yes, Alice, thanks for the introduction. Today I'm here to talk a little bit about one of the applications that we use Knime for here at Idorsia. For those of you who do not know much about Idorsia, we're kind of a mid-sized traditional pharmaceutical company. We're half startup, half well-established. The company name Idorsia itself is quite young, only about 3 years old, but for Actelion, and our R&D division was spun off from Actelion when Actelion was purchased by Johnson & Johnson. So now we're based in Basel, Switzerland, along with many other pharmaceutical companies. We have about 1,200 employees, and it's been a very exciting year for us as a company, as we've had two approvals and one positive phase 3 result, which are our first three big products that we're going to have on the market soon. So that's a company. I'll get into a little bit more details about who I am and what I do. So my name is Aaron, as been mentioned. My background is in biochemistry, and I done a lot of work on flow cytometry data analysis and cell counting. After that, I joined Knime, as was mentioned earlier, as a support engineer. I see some familiar faces or familiar names in the chat. So, for example, hi Peter. I hope you're still here. I'm the team leader for what's called the automation team within scientific computing at Idorsia, and my team in particular works on a lot of scientific workflows. We build the pre-processing pipelines for our genomics activities. We're working on sort of omics data integration challenges. I have a couple of chemists on my team who are building these ultra large scale virtual screening systems, which use some interesting methods to screen like very, very large data sets. I think we're around in the billions of compounds we're screening there. And we do many other like one-off data analysis projects. I don't say one-off lightly, they're all interesting, and one of them is what I'm going to be talking about today. So my team works within the larger scientific computing group. Generally speaking, we support drug discovery for all sort of computational activities, including data management and workflows and software engineering. We work in biology, chemistry, and pharmacology, so quite a broad scope of activities. And strategically, I think one of the key things that we're really aiming for is just to make sure that the Knime's or that Idorsia's data is sort of fair, which is an industry acronym which stands for findable, accessible, interoperable, and reproducible. And so today, because we do have such a large scope on our team, I'll talk about we work kind of in this up to the end of the blue line here, but really all the way back towards the beginning. But today specifically, we're going to be talking about animal models and developing animal models and how we have done one pretty interesting task for that in Knime. So one of the areas of interest that we have is around aging and specifically around dealing with behavioral disturbances which come with age, which are unfortunately quite common. Probably many of you, including myself, have had some experiences with this. It's extremely unpleasant. There are no good treatment options, and also, you know, for this, in order to develop therapeutics which might help in these disease areas, we need some animal models in order to deal with this. And one of the animal models that we're working on developing is the use of these SAMP8 mice, which is a special strain of mice that shows accelerated aging. And part of this includes some brain atrophy and cognitive decline. So this is, in theory, at least, it's a nice model for us to use for exploring some of these psychiatric symptoms that we're interested in. So agitation is one of the key symptoms of this, and what we're aiming to do here with this model development is to use these what's called reactive aggressive behavior in mice, and to use this to see if it's has some translational relevance for agitation. So practically speaking, what does this mean? Okay, it's a lot of foundation, but what we're talking about at the end of the day is that we have a SAMP8 mouse, which is the white mouse. And we use something called the Resident-Intruder paradigm here, where we introduce a second mouse into the white mouse's enclosure. We monitor the mice for a period of 10 minutes, and we sort of quantify the amount of aggressive behavior that we see in that time period. And we use that as a proxy for how agitated the mice are. So the way that this is sort of traditionally done is by manually scoring the videos. So you can imagine if you're doing a large animal study, which could have up to 100 animals in it or something like this, maybe 40 animals, but over many time points, what you'll see is that the manual scoring of the videos is extremely painful. So it takes actually at least 10 minutes to score a 10-minute video. And if you have 100 of these to do, you're going to be spending a lot of time in VLC, clicking next frame, trying to be as accurate as possible with your annotations of the videos. There are some existing CV methods for this type of work that are available. Our experience with them so far hasn't been great, mainly around the fact that getting really robust posing models for mice has been difficult for us. We're not domain experts in this area. There are probably people who are better at it than us. But rather than giving up entirely on the approach, we decided to see if we could use a pose-free model for monitoring the aggression of mice. Okay, so the goal here is, if we look at this picture on the left, we've got two mice. Maybe at some point in time, they start having some aggressive encounters, right? And we want to measure this. One of the really difficult things about this task is that actually the aggressive events are very rare. And the training data, as I mentioned, is quite hard to come by. And then also another major challenge is actually that the behavior is in the time domain. So looking at single frame classification isn't really sufficient. So what you see is, in this picture on the bottom here, you got two mice. Are they hanging out? Are they kissing? Are they fighting? You don't know, unless you see their behavior in some context, and this context happens in the time domain. So single frame classification doesn't work very well. Here's an example just of what kind of some of these aggressive events look like. And you can see over a 10-minute period, you actually only get about 7 seconds worth of aggression. So for 99% of the time, the mice are peacefully cohabiting, but what we want to measure is that 1%. This is also probably the main challenge in building the model, as I think Emily mentioned. When you're looking at rare events, yeah, you have to have these receiver operator characteristics, and one of the main challenges about having these very class imbalanced problems is that your AUC, this number she defined earlier, it has to be really, really high for the model to work. So sort of the key insight or difference in our algorithm from other attempts to this that we've found about is that we're actually not learning on the pictures themselves, so not the individual image frames, but we train our convolutional neural network actually on the differences between consecutive frames. So rather than having 3 channels RGB, which is sort of the typical way that you would do an image classification, what we do is multiple time lags. So we do the difference between the current frame and the previous frame, and then the difference between the current frame and the -2 and the current frame -4. And we use these as our layers for training our channels as inputs for our convolutional neural networks. I won't go over CNN architectures. I think either you know what it is and already know how it works, or you don't know anything about it and don't want to know how it works. If you're in the middle, there are a lot of great other topics on, or explainers on how CNNs work, but I won't get into that now. The really cool thing about this approach is actually that we were able to build a very compact model, so only about 10K parameters. If you're familiar with ImageNet or some of the other standard approaches that we've used, they have millions of parameters, sometimes tens of millions of parameters. But actually, we were able to do quite powerful classification of these behaviors using a very, very small neural network. The key being learning on the differences between the channels and not the channels themselves. Okay, so here's an example of what our model is actually learning on. You can see here, these are they're kind of funny looking to make into a video, but you can see some shadows of the mice, and you can see all of the signal that's coming in the video is really around the movements of the mice, and you're not getting distracted by anything else here. This is very sparse training data, so there's some tricks for weight initialization. I won't get into those details now, but they were also important in order to get things to work. So going back into our machine learning results here, I can show you some examples of how our model works. So here are some ROC curves that show that, like, generally speaking, our AUCs are in the better but not perfect category, as we saw Emily explain in her slide on the topic. The models are pretty good, especially considering that the events are quite rare. This is good. It's not perfect, so there's some false positives, and there are some issues that we have around tuning and optimizing the fight detection. We don't really have time to go into that too much, but Knime was very helpful in sorting out those problems. The key takeaway, though, is that our model correlates to manual scoring, and that we are able to observe experimental effects with the model, the differences in between treatment groups, as we could see with a manual analysis. So this is useful as a data analysis tool. Okay, so how do we actually do anything with this in Knime? We have this kind of internal reference architecture that we use a lot, using this concept of guided analytics, which you've maybe heard about if you've been following Knime's stories about how to use their commercial products. The web portal, the Knime web portal, is really a key part of this this process for us. A typical sort of guided analytics architecture for like large scale compute jobs, which we do quite often, is that we'll have some bench scientists interacting with the Knime server. They'll find some data in our local data repositories, which are linked to our lab notebooks. So they upload their data onto their lab notebooks, they browse for it in Knime, and then when they find the data that they want to submit, they can just drop it into a queue on AWS Batch and upload the data to S3 so that the batch jobs can read and write the data easily to the S3 directories. Knime does all of the orchestration and gives the results back to the end user. So how does this look practically speaking? We have this sort of Resident-Intruder computer vision tool, which we have deployed on the web portal here. And what it does is, as kind of explained in the reference architecture, it reads the data from our raw data store, it validates the videos that we wanted to select, it caches the results into S3, runs the inference, gets the results back, and then does a little bit of peak detection and presents the results to the user. So we use BERT to generate a summary here, which shows these line traces, which show the model probability and the detected aggressive events. We count them, count the duration of them, and a few other metrics. And all of this ends up in this nice web experience here, where they put in their parameters for doing the data selection, they pick their data files, and then the workflow runs and they get their results. So there's some cool features of this. We use spot instances in AWS on our batch queue, which allows us to really run very inexpensively. The other cool thing about working with AWS Batch is that it scales to 0. So you don't have idle costs associated with having the application running. So the only thing that's always on is the Knime server. And when we need 100 GPUs to score the results of some study, we can just drop the jobs onto the queue, and AWS will spin up the GPU instances that we need, and we can score 10 hours of video in 30 minutes for about 5 Swiss francs, using 8 hours of compute time in those 30 minutes. So this is quite a slick solution here for us. It's okay if we only use this tool every once in a while. Once it's developed, it's sitting on a server somewhere, and it's just ready in case anybody ever needs it. Okay, so that's everything I wanted to show you guys here now. Of course, I have to acknowledge a few people, mainly in the CNS group that actually did the experiments. So there's Giorgio and Hélène, Sean, and Michelle, who are organizing the actual lab work, and then it was me who was doing the software engineering. So really, a lot of the hours spent on this were not mine, but theirs. So, anyways, I would end here and open it up for questions if there are any.
Yeah, hey Aaron. Well, I would have been very sorry not having you back, because this was a very interesting presentation and very diverse from the others that we had. And yes, we already have a question in. So as a reminder to the others, please use the Q&A session. I believe that was like a fantastic presentation. Write your questions so my colleagues can transmit it to us and ask Aaron about this. So the first one is about the mice. So on the video, we see that there was a gray and a white mice. Does the color of the mice play any role in the analysis? Does it impact your algorithm at all?
So yeah, it's an interesting question. The mice were deliberately selected to be different colors originally, but not for a purpose that we currently use. So the original thinking behind this was that it would be easier to track the mice when we first started working in this area. If one of them was black and one of them was white, there would be never any confusion about which mouse was the SAMP8 mouse and which was not. This, in theory, makes doing all of this posing stuff easier, but in fact, not easy enough. So the posing is still very difficult to have working in a robust and automated way. And for that reason, we switched to using this pose-free model. And in fact, we're really looking at differences at the absolute value of differences in frames. So I think the color of the mice in the end is not that important, and that this would work equally well with 2 white mice or 2 black mice.
Mm-hmm. Okay, I believe that's a nice side effect of, of this algorithm. That's fantastic. We have another question on how big your training data set was. Can you talk to that?
Yeah, it's a good question. So we had, I think, around a dozen videos manually scored. Each was about 15 minutes long. So it's quite a physically large training set when you go from, I mean, when you start with a video, you don't think of a 10-minute video as being very big, but actually when you expand it out into array size, it's quite large. So we do, a lot of downsampling and reduction and compaction of the data into this sort of sparse format, which is nice. But yeah, I would say a few hours of video scored manually at the most.
Okay, fantastic. There's another question coming in.
One small point I would add there is that actually we did the learning curves on that as well, and we found that marginally we were not getting much improvement in the performance of the model as we added more training data to it, at least within the experimental setups that we had. So.
Okay, fair enough. Okay, the next question is, do you think that you gain also accuracy with machine learning compared to the manual counting? Do you have any data on that? Did you try to score?
So far, I would say the data, this is kind of ongoing work that we're working on. I would say very clearly less accurate, at least so far. It's really a difficult problem because of the sparsity of the aggressive events. But the goal of this system was not to build a more accurate model, but to build one which takes less time to work with. So if we're still able to get reasonable p-values in our experiments, we don't ultimately care too much how quote-unquote accurate the model is. There are lots of, and I put this accurate in quotes because it really depends on what you're trying to optimize. I mean, if you're trying to perfectly mimic what a human does, that's one thing. But when you're talking about experimental biology, what you're probably more interested in is there a compound effect? And for that, accuracy becomes complicated, let's say. Complicated concept.
Yeah, I fully get it. Let me, as probably one of the last questions we can pose to you, try to merge 2 questions. One is about the double checking. So did I understand correctly that the scientists will upload the videos and get out the frames with the aggression behavior to further examine those?
Yeah, I didn't show this in the workflow description, but actually one of the outputs that we generate are, I kind of refer to them as director's cuts of the videos, where we show, and that's kind of what we have here, where we extract all of the detected events into a smaller video, which in this case is only 7 seconds long for this one. And we've got the labels here, so you can see that we're really only, and the frame indexes and the times, so they can actually cross-reference this back with the original videos to see if there's anything going on here. But this video here would show all of the events that were detected by the computer vision model. The other sort of key part about the manual validation, because it's really very important, are these line plots here where we show the model confidence. And this also gives you some intuition about how well your model is behaving. If your model is spiking quite a lot, that might be a good indication that you need to have a closer look at this video to see if maybe something's gone haywire with the scoring.
Okay, fantastic. The other question that I wanted to merge to this one is that what kind of data are you exposing to your end users? But is that all that we're seeing in this slide, or do you have anything else that might be important to tell or show?
Yeah, I would say, I mean, so we report these 3 metrics. We have it in the BERT report, which we use for kind of just quality checking of the data, and then we generate a flat file, which is ultimately, integrated back into our systems with the summary statistics for the run. And then this is then used in downstream statistical analysis.